All right, shall we get started? Or more like finished with whatever I started the last time. So let me quickly say where did we end the last time. So what I did, I showed you that the implicit Euler can be written as an optimization problem, meaning so implicit Euler can be cast into a problem of this form when you are minimizing some function g with some x, where x is of course a vector, the g is just a scalar function. And we also have we usually assume some good things about g, like being twice continuously differentiable, that it's usually we assume that's convex. We know that's not the case in physics, but most optimization, so in general optimization is about minimizing multivariate functions like this. And I think where I ended the last time, so let's just pick up right there, and then I will explain you what can we do for non-convex functions as you encounter in phys-based simulation frequently. So we talked about descent methods, right? just a quick recap about descent methods. So descent methods always work. If you came late, you didn't really miss anything. I'm just saying what I said before. So descent method, they first pick a descent direction. And then they find a step in the descent direction, t greater than 0. That's how far we go in that direction. They are iterative methods. You start with some initial guess x0, then you make one step, then compute a new descent direction, do another step, and so on, hopefully eventually converging to x star, which is the solution. Where the solution, how do I tell the solution? That the gradient of the function g at the solution is 0. Okay? And we talked about two main descent techniques, the most obvious one being gradient descent, so let's call it GD, like gradient descent, where you just go in the negative direction of the gradient, okay? And the last method, the one that's most frequently used in phys-based simulation and probably everywhere else too, is Newton's method. So Newton's step, the direction is x and t. So the only difference is in how you pick the descent direction, okay? The line search technique is always the same. Is this sharp enough? There. Yeah. So in Newton's method, what was that? Do you remember? It was similar to this, except that we changed something here. So we put the inverse Hessian there. And I think that's what we ended the last time. I was explaining where the inverse Hessian came from. The bunch is not here, but he was asking that very good question. Okay. So then the question, and I also mentioned that on the textbook example of minimizing a quadratic function which can be skewed funny, Newton converges in one iteration, right? Obviously, Newton converges in one iteration on a quadratic function because it's doing a locally quadratic approximation. The function already is quadratic, it just solves it in one step, right? In that case, the t actually will be exactly 1 because it will shoot right down to the solution. But the more interesting question is what happens for general nonlinear functions like the g that comes from implicit Euler. And here is a typical convergence plot of Newton. If you look at the convergence, so what is a convergence plot first? So on the x-axis, we would have the number of iterations. So this is the x0, x1, x2, and so on, however many iterations we are doing. And on the y-axis, we would have the residual. So the residual would be the value of the objective at the current iterate minus the value of the objective at the solution. So the gx star, that's the absolutely smallest value you can possibly get there, right? We are assuming that the function g is bounded from below, because otherwise we could be going to minus infinity. That would be weird. So we assume there is some minimum, and so this is the residual. And typically, if you are looking at these convergence plots, you would do a log plot. So on the y-axis, this would be a logarithm. So it would start with 1, then here would be something like 10 to minus 5, then there would be something like 10 to minus 10, and 10 to minus 15. So that means once you got the residual to 10 to minus 15, you're like almost sort of like on the machine precision. So you don't really have to be converging any further because that's as good as it gets, right? And if you look at the convergence plot of Newton, maybe first we can think about the convergence plots of gradient descent. Do you know how do they look like typically? They look like something like this, right? So you can think about it something like the residue will get multiplied by something like 0.99 or some coefficient like this, right? This is on a log-log plot, so it like goes. If you want really accurate solution, it's going there very slowly. You know how Newton typically looks like? So this would be the gradient descent. What Newton typically gives you is an interesting thing. So it starts something like this, and then it rolls over and goes very fast. So this is called the two phases of Newton convergence. The first phase is the linear phase, where it behaves sort of similar to gradient. That's probably not a correct statement to say that it's at least the error or the residual reduction or error residual reduction is similar to gradient descent. And at some point, interesting thing happens. At some point, Newton enters what's called a quadratically convergent phase. We write it here. Quadratically convergent phase. And once it gets there, then it computes the solution up to machine precision almost immediately in like 5-6 iterations. Because at this point, the error reduction is quadratic. You can sort of see it in the log plot. So here it's like a line, and here it's parabolic. So here the error drops very quickly. In most, does that make sense? So the two, there are some quite cool theoretical analyses of Newton's method. Are you guys okay? Am I making sense? Okay, you can read lots of interesting theoretical analyses of Newton's method. They actually compute it just using math without. This is like these graphs are when you are looking at typical optimization problems. Okay, that's what you typically see. But you can do it in theory, and you can also in theory you can verify that there's a linear phase and quadratically convergent phase. This is the base or the classical convergence analysis. You can read, if you want to read more about this, go to Steve Boyd's book or the online course. You will get a lot of details on that. Then there are some other convergence analyses of Newton using self-concordance, and which is a more advanced way to analyze the convergent behavior. So we don't need to go in too much crazy detail. I just wanted to mention this. The linear for most problems. Do you have any questions on this? No? For most problems, the linear phase is also pretty fast. It takes, altogether, this usually takes something like 20 iterations, but not always, okay? Even for convex problems, you can actually find cases where Newton converges slow. It's not common, but it can happen. I just wanted to warn you a little bit. Do you know when that happens? When Newton really struggles to get a solution. So Newton is sort of like the gold standard, the standard workhorse that pretty much everybody's using in optimization. And more advanced optimization techniques like interior point methods, they are all built on top of Newton's method, essentially. They just iterate Newton's method in a clever way. But it's good to know that Newton is not always guaranteed to converge quickly. Sometimes it can happen that this linear phase that can take forever. It doesn't happen often, but it can happen. Do you know when that happens? If you have some function, even if it's convex, but if it has, yeah?
I mean, it probably happens when Taylor expansion around the optimum misses quadratic term.
Well, yeah, once you are close to the optimum, it will always look like this, right? But the problem is that you might be too far away and getting there. So the quadratic expansion where you currently are, which is not at the optimum, if you are already close to the optimum, you'll be fine. But it could be the case, and that's I think where we are getting at, is that where you currently are at your current iterate, the quadratic approximation is not good enough. It's not too good. Okay, and that happens when? That happens when the function does this very high third order derivatives. Okay, so if you take, and that sometimes happens in optimization, even in physics, if you went into, didn't tell you about the Nell-Hookean material? That's exactly why this would happen. Did you hear about the Nell-Hookean material? It's about finite. It was in the finite elements. That's a material that you cannot invert. And this material has some term which is like squared logarithm of something of the deformation gradient, I think so. So some logarithm term. And then this logarithm term is weighted by some weight. So if you start doing things like this, then you can get in trouble with Newton converging very slowly. Like, I guess I can draw an example. Like if you have some function, maybe it's convex, right? And there is some very sharp feature somewhere, very high third order derivatives. Newton will have problems with this. Why? Because the quadratic approximations here are not a very good approximations of how the function looks like for further down, right? Okay, I think there's no need to go deeper in this topic. You would encounter it if you are going to constraint optimization or interior point methods, then this thing starts showing up. But it will also show up in physics if you are doing something like no-Hukin, some of these really advanced materials. It usually does not happen in mass spring systems unless you were crazy about the spring stiffnesses. If you had some like really supple spring and some crazy high stiff spring, maybe that could start being a problem. Okay, so that's the basic Newton method. So I guess I should say, what does it mean numerically, right? So how do we compute the Newton step? I think maybe I can just say it quickly. This comparison to gradient descent is actually quite unfair, right? Because each iteration of Newton takes much more time than an iteration of gradient descent. Why? Because in gradient descent, all you are doing is computing the gradient. But in Newton, you are also computing the gradient, but on top of it, you are computing the Hessian. And what's worse, you are also inverting the Hessian. I mean, when I'm saying inverting a Hessian, I mean, you are not really inverting a Hessian. What you are really doing, what you really want to be doing is to, let's say that H is the Hessian, okay, to simplify this thing. So that's the matrix of second derivatives of G. And what you want to be doing is solving this system. So the X and T is the unknown, and you want to be solving this system of linear equations. Okay? This is the unknown. This is the gradient, right? That's what we have here. This is and the H is the Hessian, which is a sparse symmetric matrix. Okay. The one problem is that both the Hessian, of course, and the gradient, they depend on the current state, right? So after you do one iteration, so it works like this: you compute the descent direction, then you run line search that computes the t, then you advance to a next state, so you would go from x0 to x1, and then x1 you have to compute new Hessian and new gradient, and rinse and repeat the entire process. Yep.
Sorry, it sounded a little bit like Jacobi.
Jacobi. I mean, they are all iterative methods, so there is some similarity. Yeah, my point here was that these things change at every step. So at every step, this was my point, at every step of Newton's method, you have to be solving a sparse system of linear equations. All right. And what is a problem? The Hessian has to be always symmetric, right? We had that. You know why? That's because how the mixed partial derivatives work. It doesn't matter if you differentiate first with respect to x and then respect to y, or first with respect to y and then respect to x, right? That doesn't matter. That's why the Hessian is symmetric. Now, what is going to be a problem if you run this on? So if we return back to physics now from optimization, and our function is, that's what we derived the last time, is the 1/2 x minus, you know what, let me do this on a separate piece of paper. So let's go back, how do we apply this to physics to get a really robust solver for implicit Euler? So the form of the optimization problem we derived the last time looks like this. Plus h squared ex. And you should tell me if you remember from Monday what these symbols are. So what is the x? That's the next state. That's what we are solving for, right? If we are simulating our time steps, t0, t1, and so on. So we have simulated up to here. Then we are computing the next one. The state there is called x. Maybe a tn plus 1, whatever. What was the y thing? Does anybody remember? That's the explicit Euler without forces. It's the pure inertia, pure inertial motion. Remember, I was saying that if there are no forces acting on an object, it just happily floats through space, right? The reason why objects don't do it here, because we have gravity field and we have air drag, right? But if you are in space and you have some initial velocity, just keep going. That's what the y is. What was m? Mass matrix, that's right. H time step, yeah, so it's a scalar, right? 0.033, that's my favorite one. And E is what? The energy potential. So it could be a mass spring system. That's the easiest potential you can think about. That makes a lot of sense. Plus maybe gravity potential and what have you. Okay, so what we want to do is apply Newton to this particular problem. Okay. And if you look at the two terms, we see immediately there's going to be a problem. This first term is fine. That is convex. Because we assume that the mass matrix in the simplest case is just diagonal. In the more general case of finite element method, it's not diagonal, but it's still symmetric and positive definite. Okay? And the y is a constant here, right? So this is just a convex quadratic function. But the problem is that this is not convex. Already for this really simple system of two springs connected with mass points, already there it stops being convex. Did I show you this example before? I think I did, right? Actually, I showed it somewhere for sure. So if this is my system, as simple as this, that's the current state of the system. These are three mass points, two springs. I did show this before?
Where it's in the middle.
Yeah, exactly. So okay, I'll just do it really quickly. So this is one state. This is another state. These are the rest lengths of the springs. Okay, so this is 0. This is 1. So the energy. So I'm interpolating between the state 0 and the state 1, and this is the energy. The energy is 0 here and 0 here because the springs have rest lengths there. But if I do linear interpolation, at the middle, I get this. So this should be on the same line. So in the middle, the energy goes up. Okay. So the energy ends up doing is something like this. Whoops. Because then if I keep extrapolating, if I do like this, then the energy again goes up, right? Because I'm stretching the springs. Okay. So if you see something like this certainly cannot be convex, right? If it was convex, it would be bowl like this, but you have this hump here. And what happens if you run Newton on this? What happens? You get, eventually you still assembly or Hessian, no problem, right? And then you get a matrix H, and then you call a solver, and then you will get what? I think I mentioned it the last time. Well,
So are you asking about forces?
No. I'm asking where does the non-convexity start to bite us? How does it matter really? Where does it start complicating things, right? It has something to do with the H matrix. Okay, if the function was just convex, if I had just this part, or in general, if my g function is convex, then the Hessian is positive semi-definite, right? That's because again it's a bowl, and locally I have to get a positive semi-definite matrix. But if it's not convex, so if I'm summing a convex and non-convex function, then certainly I will get the non-convex function in general back, right? Because the non-convex contribution ruins the convexity of the first term, like spoils the whole function. So what happens here is that the H matrix can be indefinite. It can happen actually quite quickly, right? Think about it. What does it mean here, right? If your iterate is somewhere here, Newton works on this no problem, right? Like one-dimensional Newton iteration, right? What Newton does, it establishes the local optimal quadratic approximation, and then the direction wants you to move with t equal 1, you would move right here, right? But what happens if your current iterate is, for example, here? It still establishes the locally optimal quadratic approximation, but in this case, it looks something like this, right? It's actually upward down. So what do you think Newton will do to you in the non-convex case? It will do something terrible. It will actually push you not to the minimum, but it will actually increase, right? It will go to the critical point of the local quadratic approximation. And that's the wrong way to go. So indeed, if you have a non-convex problem like we have in physics, Newton can, if you just, you can with a good solver, you can even solve it for indefinite system, unless the system becomes singular, right? Then you get in trouble, then you can't really solve it, or at least not uniquely solve it. But if it's just indefinite and not singular, full rank, then you could solve it, but then the solution would not be very nice because you could get an ascend direction. So instead of minimizing it, what you want to be doing is minimizing this. Instead, you could be maximizing, exactly because you are in this funny region where the quadratic approximation is essentially wrong. It's even pointing in the wrong direction, okay? So to make this work for physics, for deformable solids, we need to do something about it.
Can I ask a question?
Yep.
Would the gradient descent method behave correctly in that?
That's a great question. Thank you. I should have mentioned it at the first place. Yes, the gradient descent would behave correctly in this case. Correct. The gradient descent always does, right? Because the gradient points after you do the minus in the direction of the steepest descent, right? Regardless of whether the function is convex or not, right? The only exception is if you are already at the minimum and the gradient is 0, then it doesn't point anywhere, but then you are done, right? In the non-convex regime, the name of the game is to just find a critical point. Yeah, you basically gave up on solving the problem in a global way. that's almost impossible. So yeah, and that's also an idea how to actually fix it, right? If you see that Newton is giving you absolutely crazy direction, that will give you a direction that increases your energy as opposed to decreases, you could actually fall back to gradient descent, which always works, even in the non-convex case, right? Now, the problem is you don't want to do that because of this reason, right? Because gradient descent converges painfully slowly, even for the convex case. So you would end up doing tons of iterations. We actually tried this at Tintin at some point. By the way I'm going is then towards explaining you our fast mass springs paper. We will get there in a moment. That's sort of where we are headed with all this. But first, I will tell you how to solve properly how to do the Newton's method, how to fix the Newton's method so it supports even this non-convex problem, which arises from physics of deformable solids. Okay. Yeah. So what you said would be one correct solution. That would already be a correct solution. Actually, that's quite good, right? But what we want is not to go back all the way to gradient descent, because that would mean the convergence would get much slower. Okay. So do you have some other idea what to do? I can tell you the usual trick that people do. By the way, once we are at this non-convex regime, then we are outside of the realm of convex optimization, where everything is nice and beautiful, and you have like these nice books that explain well-studied and proven methods. So this is more of a street fighting technique. That's how Steve Boyd calls it. But I can tell you one that works quite well, that people have been using for this case, for the physics of deformable solids case, and it's quite effective. The idea is regularization. You might have heard this before because it comes up in all sorts of different contexts. I guess the general idea of regularization, if you are dealing with some unwieldy matrices, you just make them better. And the easiest way to make them better is to just add a multiple of identity. Sometimes it's called Tikhonov regularization. I think it was some smart Russian guy who came up with this. Tikhonov.
Oh, okay.
Am I saying it right? Tikhonov. Yeah, it's our Russian connection there. So the idea is simple. If you don't like your h, if your h is giving you trouble, if the h is indefinite and giving you ascend directions in Newton, then we will make it behave by adding a multiple of identity. Well, alpha is a scalar, which is presumably positive. Okay? And I claim that I can always find an alpha to make this matrix positive definite. that by doing this, if I take big enough alpha, I can make it positive definite. Do you see why? So the H is symmetric. It's a real symmetric, potentially indefinite, a real symmetric. Let's assume it's indefinite matrix. By adding a multiple of identity, I can make it positive definite. If you are paying attention during your linear algebra classes, you should know why why this is always possible. So okay, let me explain that. Because the matrix H is real and symmetric, I can do eigen decomposition. But this is nothing that you would be actually computing in your code doing physics. This is just to show you that the alpha. This is like a proof of a statement that the alpha exists to make this matrix positive definite. So you would do eigen decomposition, where Q is the matrix of eigenvectors, lambda is the diagonal matrix of eigenvalues, and Q transpose is a transpose of Q. And that will that always exists and is real because the matrix H was real and symmetric. This is what you know from linear algebra, I hope. If not, I will not be explaining it today, but refer you to linear algebra textbook. We do this in EAS 205, by the way. And so what happens now? You might already see what happens if I add a scalar multiple of identity. Then I can do this cute trick that the identity can be certainly written as Q transpose, because the matrix Q is orthonormal. And from this you see that what I'm actually doing here is plus alpha identity here, right? So this adding the multiple of identity is actually directly adding to the eigenvalues, okay? So all you need to do is if the eigenvalues, if you do this in MATLAB or something, they typically come ordered. So the last one is the most negative eigenvalue. So you just pick the most negative eigenvalue and you pick the alpha so that it's larger than the most negative eigenvalue. And if you do that, you are guaranteed that all these are positive and your matrix is positive definite. Okay, sure. This part here? Okay, I could even write it with symbols, but that would be only more confusing. And this is just like a proof. It's sort of silly. This is just to convince you that I can always pick alpha to make this matrix positive definite. Okay, using eigen decomposition, I can get it to this form. So what the alpha is doing is directly adding identity to the matrix of eigenvalues. This lambda is a diagonal matrix of eigenvalues. The problem is that some of the eigenvalues might be negative. That's why the matrix H was indefinite. If it wasn't, if all the eigenvalues were already positive, we wouldn't be doing this. Everything would be already cool, right? And here I just picked the alpha big enough to make this diagonal matrix positive. That's all. Okay, so we do this, and we in the Newton step, where previously this was the Newton step, the original unmodified Newton step. And what we do instead is we stick in the regularization there. So then we solve for, maybe I should be calling it like a regularized Newton or something, whatever, minus gradient of G. So then you solve against this. Okay. The other advantage of this is there you can use solver that assumes the matrices are positive definite, because some solvers actually assume this. Like if you are running conjugate gradients or your favorite Jacobi, I think they assume it or they behave better if the matrix is positive definite. So that's actually another advantage of doing this. Actually, if you are doing which I usually recommend here is to do sparse direct solvers. Unless you are doing some crazy high resolution multi-graded thing. So unless you are doing something crazy, I recommend sparse direct solvers. And if the matrix is symmetric and positive definite, the right one, the easiest one, the most lightweight one is sparse Cholesky, just direct sparse Cholesky. There are variations on it that can handle indefinite matrices and so on, but they get a little bit more tricky. So if you can just get away with sparse Cholesky, that's the best. And if your matrix is guaranteed to be positive definite, then you can always do that. Then the Cholesky factorization will exist. If you want it to be factorizing indefinite matrices, you have to do some LDLT decompositions. It's possible, it's just a little bit more complicated and a little bit more costly, I think, if I remember correctly. Okay. But what this will mean? What does this? So first of all, if you do this, this works fairly well. At least as far as I know, that's the state-of-the-art technique, how you deal with the non-convexity in physics. If there are some better ways, let me know. That there might be, but I'm not aware of that. It's because this is fairly uncharted territory, because the convex optimization people sort of punt on it. I may be wrong. There might be something. But at least in the most, I can tell you, this is a correct statement. At least in the most recent SIGGRAPH papers, this is what people would be typically doing. So yeah, what does it really mean? What does it mean if alpha is 0? That means I'm not regularizing at all, right? Probably because my H already was positive definite. And if I keep increasing the alpha, what's gonna happen to my Newton direction? What if I bring alpha? Imagine for a second that somehow I managed to bring alpha all the way to infinity. What happens in the limit? What do I get in the limit? Or imagine, think about it this way. What if the alpha is so big that the influence of the Hessian becomes completely negligible? Exactly. Then it converges to gradient descent. Exactly. Because once the alpha trumps the Hessian, then you are essentially back to gradient descent, right?
But wouldn't the alpha terms stay like this?
Yeah, you're right. The alpha actually only makes it worse, because the alpha is only telling you to do smaller stat. But your line search could potentially override it, right? Now you would have to be a little bit careful about the line search. Yeah. So there might be some nuances there. The other question is, how do you actually pick the alpha? Where do you get the alpha? You probably don't want to do the eigen decomposition, because by the time you did the eigen decomposition, you went to dense matrices, so you spend much more time than you would need to actually solve this. So you definitely don't want to be actually computing this for. That's right. That's a great idea. What we did with Tintin when we were implementing this, we just did a super simple thing. You don't have to get the very smallest alpha that does this. You can just get a sum. And what we did, we just did like a really stupid search. We just started from some alpha that's really small. Then we always multiplied by 10. And when we tried the sparse Koleski, and if it succeeded, we knew it was big enough. That's probably not the smartest thing to do. It actually worked fine. Okay. And if you do this, you get a really nice, robust implementation. So that sort of concludes this chapter. So what we did, we converted implicit Euler to an optimization problem. Then you can apply Newton's method with some precautions to handle on convexity, and that gives you a really nice and robust solver. That's goal number 1 accomplished. Okay. But that's not all we can do with this variational formulation, and that brings us to these 2 papers which I wanted to tell you about. Those are results of our recent research, the fast mass springs here with Tintin, and a generalization of this. So actually, let me give you a little bit of story. This is the idea just for mass spring systems, and that's what I will explain you in the rest of the lecture today, how this actually works. The idea is to take this optimization problem and solve it in a little bit different way than using Newton. And that little bit different way turns out to be similar to position-based dynamics in some sense, actually a little bit better than position-based dynamics in some sense. And it turns out it's very useful, especially for real-time physics. But this paper was limited to mass spring systems. So what we did later, we generalized it to more general continuum-based constraints. Yep.
They kind of, combined all the different solvers into one now.
Who did? You mean the Flex solver by the NVIDIA guys?
Yeah.
Yeah.
That's a great question. No, these solvers are actually more advanced in some sense than the Flex solver. The Flex solver is using only PBD. And this stuff, it will be more clear after I actually explain it. This stuff has a little bit more powerful solver in it, which makes it converge faster than PBD. This would probably, I could spend another lecture explaining how PBD relates to this. Or I can say it quickly, actually, that will probably be nice. PBD, position-based dynamics, can be interpreted as a different, almost correct way to minimize this. Okay, that's not how PBD was originally derived, but once we came up with these papers and Matthias Müller started thinking about this, and he came up with a way to, or we also did, there is a way to tie back PBD to this. But the PBD does not exactly minimize this. It does something close to it, but not exactly this. So it gives you something like implicit Euler, but not exactly. And the flex paper you were talking, the unified particle physics thing, it's very cool because it has the fluids and so on, but it's just a generalization of the PBD ideas. This goes in a little bit different way. And first, it really solves the implicit Euler problem perfectly without doing any hacks or anything like this. And second, it's a more efficient solver in the sense that it converges faster than PBD. It's a little bit nebulous statement because it doesn't converge to the same thing as PBD, because PBD doesn't converge to the right thing to begin with. So it's a little bit tricky to compare, but at least roughly you can say that this converges faster. And I will explain why, because that's what I'm going to explain now. Because that's another application of the fact that you can write the physics of deformable solids using implicit Euler as this optimization problem. Okay, are you ready? So let's do that. So as I said, the first work, and that's all I will be talking about today, only applies to mass spring systems, but they are already quite interesting. And all the difficult nonlinearities and non-convexities, they are already there, even in this trivial mass spring system, right? So I argue that's an interesting enough case to study for us. So the key idea of this work was to reformulate this optimization problem in an interesting way. So the hard part, all the hard part is hidden here, right? And in the mass spring system, this E is just the sum of Hooke's laws, right? I keep saying this all the time. I hope you remember this. Let me take another paper. It's really fun. It took us quite a while to get it right, but I think finally we got it right. So Hooke's law, that's, let me write it one more time. 1/2 for one spring, right? So P1 minus P2, those are the endpoints of the spring. R is the rest length, K is the stiffness, right? And the sum of these things for all the springs, that's what comprises this term. And that this term is the sum of these Hooke's laws for all the springs, right? And that's also what I was showing here, right? This energy here is the sum of the Hooke's laws for these two springs. And the key to the reformulation that will give us a better solver than Newton's method is the following statement, or I can put it, I guess, as a lemma, like just a tiny piece of math, not very complicated. And the lemma says that we can rewrite Hooke's law in the following form. So up to the 1/2 K, up to the scalar, this is exactly Hooke's law. And here is the whole trick, to write this as a optimization problem. And the optimization problem will have some variable d, and we'll explain what it is in a second. P1 minus P2 minus d squared. Okay. So here what the d is just, if we are in 3D, that's just a 3D vector, right? Here we're looking at just a single spring, okay, as simple as that. And what this lemma says is that we can rewrite the Hooke's law as a solution of this constrained minimization problem, where the d is the parameter over which we are minimizing. The P1 and P2, those are the fixed spring endpoints, or whatever. And after we minimize this, we get exactly the energy according to Hooke's law. Okay, is that clear what this says? Okay, so how we prove it It's like a tiny, tiny piece of math. So first, allow me to introduce this simplification of notation. So instead of writing P1 minus P2 everywhere, I'll just write P1, 2, okay? So the first thing we can notice is that, so let's look at the objective we are minimizing here. It's like sort of beautiful, it's all about optimization, right? We are just sort of doing exercise and optimization, which helps us do physics in a better way. So if I look at the objective, so P1 minus P2, I said that's P1, 2, so this is P1, 2 minus D squared. So I've rewritten the objective, okay? And this is just a squared norm of a vector, right? So I can expand it like this. So I have minus 2D transpose P1, 2 plus the squared norm of D. But I have this constraint that the norm of D is R. So the D squared must be R squared, okay? And here I will use the Cauchy-Schwarz inequality, which sounds fancy, but it's a simple thing. It just says that the D transpose P1, 2 is less than or equal the norm of D times the norm of P1, 2. The norm of D again being R, right? Because the hard constraint, my optimization is that the norm of D is R, okay? So if I plug in the Cauchy-Schwarz, it goes, if I multiply by minus 2, so the inequality reverses, so this will be actually greater or equal this. So here I will have P1, 2 square minus 2R norm P1, 2 plus R squared, okay? And do you see where I'm going with this? Maybe there is there certainly is a faster way to do this, but I think this one is more natural way to derive this. Do you see where I'm going with this? I'm going to P1, 2 norm minus R squared. Oh, without the square here. Okay. And this is what we have here. So this is a lower bound on the objective, assuming this constraint is in effect, which it is. So that's good. This says that the objective can never get below the lower bound. And to finish the proof, I need to just find one D that satisfies this constraint and gets us exactly to this value, right? Once that's done, then clearly the solution of this optimization problem is this, right? So the D I need to take is sort of obvious. So I define a D to be R times P1, 2 divided by norm of P1, 2. And after I do this, so I define this D, and let's compute what's the value of the objective for this particular D. Okay, so I plug this in here, and I will get this. So I will get P1, 2 minus R times P1, 2 divided by the norm of P1, 2. This whole thing squared. So I took this objective, and I plug the D in there. And what we can do now is write it like this, P1, 2 divided by norm of P1, 2. So here the first term will be the norm of P1, 2. That's this one, minus R norm squared. Okay, so I just put this term outside of it, or you can just like multiply them together and it's the same thing. Now, norm of this, of course, is 1, right? And norm is multiplicative. So the norm of this is exactly equal to the norm of, I can just write it like this, P1, 2 minus R squared. Do you get it? Shall I explain it a little bit more? It's really just like a sequence of basic math steps. Algebra, I guess. And that's exactly what I was claiming to be the optimum, okay? So if we pick this D, we indeed get to the minimum. Here is a proof that you cannot possibly get below it. Done, okay? So this indeed is the optimum, is the minimum of the, and this is the solution of the optimization problem. Okay, this fairly simple but constrained optimization problem. By the way, notice that this is a non-convex optimization problem, right? Because what does it mean geometrically, this constraint? It's sort of interesting to think about it that way. This is saying that a 3D vector must have norm R. What does it mean geometrically?
Any vector of length R.
Hmm?
Any vector of length R.
Correct, yeah. So all vectors of length R in 2 or 3 dimensions, in 3 dimensions, what surface do they? A sphere, exactly, yeah. But just the surface of the sphere, right? They can't be inside, they have to have exactly R. So it's just the surface of the sphere, that's obviously something very non-convex, right? If you had a convex set, you would have to pick 2 points in the convex set, and the line between them would have to be in the convex set. Well, that's never the case if you are just on the surface of a sphere. If it was the sphere and the inside, if it was a ball, that would be convex, but this is not convex. So this is actually one of the rare examples of non-convex problems which we can solve exactly. There are some other, I guess I'm too obsessed with optimization at this point, but there's just a handful of very important examples of non-convex problems which you can solve exactly and efficiently. SVD being a very important example, eigen decomposition, another one. And this is essentially a similar kind of story there. Okay, so this is just like a cute little fact, but now how does this help us in solving physics? That's what you might be wondering now. Oh, by the way, first, what is the interpretation of this? What is the magical D that solved this problem? Is R is the rest length of the spring, P12 is the direction, and this is the normalized direction. So this really, the D, it's sort of simple, right? Once you give it a geometric interpretation. The P1 minus P2 is this vector. If this is my spring with endpoints P1 minus P2, and the D is just this vector projected to the rest length of the spring, right? That's my D. So can you see already the connection to PBD here? What is PBD doing with springs? It's projecting them back to the rest length, right? And that's exactly what this optimization problem amounts to doing, right? Here, the important difference here, we are talking about vectors, the direction vectors of the springs, okay? That makes a lot of difference, as I will show you in the following. So we are talking about the directions and projecting them to the rest length directions, to the undeformed spring, basically. Okay, so what we have done here, we have reformulated Hooke's law as an optimization problem, okay? What we have done before is we have reformulated implicit Euler as an optimization problem. And now the beautiful thing is that we combine that together and we get one big optimization problem, okay? So first thing I will do is I will put all the springs together. Okay, it's because this was just for one spring. Simulating one spring is not particularly interesting, so I will just quickly write down the formulas, what happens if you put all the springs together. So if I put, let's see. So let's say I have S springs in my system, okay. Each of them has a stiffness Ki, so this is spring index I. And Pi1 would be, the I1 and I2 would be the endpoints of the springs. And what I'm doing, I'm taking these objectives in the reformulated version, and I'm summing them for all springs together, okay? Because I have a mass spring system. For this lemma applies for every spring, certainly, right? So I can put and I can sum all the objectives together, right? It turns out that after some algebraic massage, you can get it to this form. I decided not to do the details of the derivation because it's a little bit tedious, but I will explain you what that means. So here the x, so here x is a vector which stacks the the spring endpoints, the P1, P2 up to Pm, or all the particles. So that would be a 3m dimensional vector. M is the number of the particles we have. And D is a vector D1, ds. That's the interesting part. So S is the number of the springs. Okay. And this vector is the direction vector of the directions of all the springs. Okay, all the projected directions. And what is in these L and J matrices? It's sort of interesting. So L is a matrix which needs to be a 3m by 3m matrix. And it turns out that it can be written like this. I from 1 to S. Here is the spring stiffness. And there is some matrix AI. I'll explain in a second what that is. Kronecker 3 by 3 identity. What is the AI matrix? It's actually just a vector because m by 1 vector. And what is in it is this. All zeros except for 1 at a position I1 and -1 at position I2.
Shouldn't there also be a constant term in the first line?
You mean here?
Yeah.
There should be, yes. I already discarded it because once we start up minimizing it, the constant doesn't matter. But yeah, you're right. That was a little too quick. What is in the J? J is similar idea. So the J is this. It's also sum over all the springs. And here you have the spring stiffness, AI, and there is some vector SI transposed, where the SI is a vector S by 1. And what is there? All zeros except for 1, 1 at position number I. Just the indicator of the spring, if you will. Okay? So I hope everybody sees that if I take an m by 1 vector, multiply by 1 by m vector, I get an m by m matrix, right? This Kronecker raises it to 3m by 3m matrix. So the dimensions they match. This is the first thing you would want to check. So to make sure I'm not saying something wrong. And how to exactly derive it? You just do a standard matrix algebra. These are essentially the selector matrices that select the P1 and P2. If you want to go through the math, you can.
The x vector.
Mm-hmm.
Are you just taking all the vertices of? Okay. And then, so is that? Are you stacking them like with x, y, z?
Yes, exactly. So if I was right to really explicitly, it would be, so these are my particles, right? P1, P2, P3, all the particles are there. There are some springs, right? So I have m particles, s springs. The number of springs will probably be higher than the number of particles, but that's cool, right? And all of these are 3D vectors. Maybe I could like give it, I don't want to go into the arrows game, but they are all indeed vectors. So I could also write as P1x, P1y, P1z. That would be P2x, P2y, P2z, and so on, right? So that's what this is. Yeah. Okay. All right. So now this is after we put there the minimization over D, then this is just a reformulation of the elastic energy. Okay. So here is this is the beauty of the thing. So I said that in implicit Euler we are minimizing this entire thing, and I reformulated the E as an optimization problem, as this one. Here I summed all of them together. So it turns out that you can solve the implicit Euler time step for the entire system by minimizing this objective. So the first term is what we saw before all the time, this one, that's the inertial term. Let me just copy that. And here is the elastic energy. And here, because of this lemma we have here, we can rewrite it as minimization over all the D's. So every Di for all the springs must be Ri, the rest length of every spring. The rest length of every spring can be, of course, different. The first term stays the same. And the second term times the square times that will become this, okay? So plus h squared 1/2 xt lx minus h squared xt jd plus some constant. Let me drop that constant, okay? Because once we are minimizing it, the constant doesn't really matter. Okay. So we can make this a little bit nicer. So the minimum will stay. The di equals ri. And what I can do is rewrite this slightly. So I can isolate the x part to do this without confusing you. Okay, I'll just do it. I'll just do baby steps. So 1/2 x minus y transpose mx minus y. I can write this as 1/2 xt mx minus xt my, there twice, plus 1/2 y transpose my transpose. Everybody's cool with that? We already done this a few times, right? You would have 1/2 x transpose my minus y transpose mx, but it's just a scalar, so I can transpose it and sum it together, getting this.
Less y should be transposed, right?
Oh, you're right, absolutely. Yes, thank you. This thing is just a constant because y is a constant, so we can essentially forget about this because it doesn't matter there. And then I can put these terms together, right? So this is what I have here. So I can put these things together. So I can rewrite, let's do it like this star here, and continue here. So the minimization here stays, the di equals ri. And here I will have 1/2 of x transpose, and then I put these matrices together. So the mass matrix plus h squared l x. That's this part, and then what can I do with the remaining? Well, I'll just copy that for now. H squared x transpose jd minus x transpose my. Okay. And now all I need to do to solve this is add there also minimize over x. 3m, right? Because that's already the variational formulation of implicit algebra. I want to be minimizing it over x. So that's the cool thing, that essentially, so this is how you can interpret this. These d's we have introduced here are essentially auxiliary variables we have added to the optimization problem. Okay, so we reformulated the optimization problem by introducing these auxiliary variables d. The variables d, they are auxiliary because we don't really care about them. What we care about is the x, okay? But the d's, they change the nature of the problem in such a way that we can apply a different solver to it. Now the problem is still equivalent, right? It's because this was exactly equivalent. I was just rewriting all the time. The problem of the optimization problem is the same, even though the formulation is quite different, right? One thing you can notice is that here, where is it here? Where's my, oh, here, for example. Here the non-convexity was hiding in the E, right? In this formulation, which I'm claiming is equivalent to it, the non-convexity is, do you know where is the non-convex? The main part of the non-convexity is here. Right? These are non-convex constraints we have there. Because the problems are equivalent, it could not go anywhere, right? It could not disappear. Otherwise, I did some simplification or something, which I didn't. I claimed that these are exactly equivalent problems. So that's sort of the interesting thing. The non-convexity is exposed here, okay? But the main point of this reformulation is that now we can use a different solver to attack this problem, to minimize this, and therefore solve the time stepping problem. So what we can do now is to do alternation. Okay, we first fix d and solve for x, and then we fix x and solve for d. Then we fix d, solve for x, then we fix x, solve for d. Then we keep alternating it This will be an iterative optimization process which will successfully minimize this function. Okay, so let me elaborate on these two steps a little bit. That's basically, then we'll be almost done. So maybe I can do it like this. Same. So in the first step, so which one will be the first? So let's say that we first fix D. Okay, so what happens if we say we fixed D? Well, the first thing that happens is that these non-convex constraints go away. We can just scratch that, right? And here the D becomes a constant. It's no longer a variable, right? Just like the Y is also not a variable, that's a constant. That depends only on the previously computed states, okay? So this problem essentially reduces to minimizing over X this thing, right? The first thing I'll just copy, m plus h squared L x minus here will be something of the form xtb, right? Where b, I just because the jd and the my, they are constants, I can just group them together to a vector b. It's a constant vector, okay? So what optimization problem do we have here? Once the d has been fixed, the optimization problem for x becomes quite simple. Because what is this? Now the b, h, l, m, they are all constants. That does not depend on x. So what type of optimization problem is this? It's a quadratic optimization, yeah. And the beauty is that this matrix m plus h squared L is actually going to be positive definite always. Why? Because the M matrix, that's positive definite. And the L matrix is a positive semi-definite. Do you know, can you see, I have it here, right here. The L matrix, remember it was defined like this. AI transpose, sum a bunch of these terms. Can you see why, this is like another linear algebra exercise, can you see why this is positive semi-definite? The positive semi-definiteness is defined by xt Lx being greater or equal 0 for all x's, right? And if I do this on the inner term, or does somebody want to say it? This is sort of pretty. You get, if I multiply it out, you ultimately get to these parts, AI transpose x, right? But this is just the norm of x transpose AI squared, which certainly is non-negative, right? So this matrix, the L matrix, indeed is positive semi-definite, which means, and the h squared, of course, is a positive scalar, right? So this entire matrix will be positive definite, aka good. Positive good, positive definite. Okay. It is constant in the sense that it does not depend on x. And it does not depend on d either. Okay. There's actually even more we can say about the L. If you know something about graph Laplacians, the L is essentially a Laplacian of the mass spring system graph, weighted by the stiffnesses. So the L is actually a fairly special type of matrix. Okay, so this is a convex quadratic optimization problem. Okay, and we can solve it by solving a system of linear equations, right? We set the gradient equal to 0, and what we get is, of course, this, right? Which we need to solve. So it looks like we didn't really help ourselves much, right? Because in Newton's method, we had to be doing exact similar thing, right? But actually, we helped ourselves a lot because here the matrix always is positive definite. And what is even bigger advantage, the matrix is not changing as the x's are changing, right? We will be iterating over the x's, so we will be getting different x's as we iterate. But this matrix will be always the same because it only depends on the connectivity of the springs. The L matrix would only change if you change the connectivity. Like, for example, if you cut your piece of cloth or whatever you are simulating. The M would change if you change the masses. But if you are only iterating, if you have only position-dependent forces, if you are changing the axis, this matrix does not change. So the sparse Cholesky factorization I usually recommend you just need to compute this once. And that's a huge advantage because then you will be getting new b's as you iterate, right? The b that will be changing as you iterate. But this matrix will be not. So what you will need to do to solve for x is to just perform back substitution, which is quite fast operation. It's not so great to parallelize, but it's fast, right? You just you just sweep through all the equations and solve for the x. It's a much easier thing to do than the factorization. So that means, long story short, the solve for d is just back substitution, aka quite fast, okay? The second part, so this is sometimes called a global step, or we put it here, global step. It's a global step because it's solved for the entire state at once by doing the one big back substitution, okay? On the other hand, if we have fixed x, what happens if we have fixed x? If we have fixed x, then all we need to do, so then this goes away, right? The x is now constant, and we are solving for the d's. So then we are back to these problems. To this is the optimization problem. We are solving for each spring, and here is what the solution is. This is the solution. Okay, the solution is to normalize the spring direction and multiply by the rest length. This projection thing. Again, recall the similarity to PBD. What PBD does, it projects the springs to the rest length. It's exactly the same idea. Okay. So if we fix x, then the local step, this is called the local step. Why is it called the local step? Because for every spring, we can do this individually. Every spring we are projecting on its own. So this is actually beautiful to parallelize. The back substitution, not so cool to parallelize, unless you know some good parallel implementation of back substitution. I don't know. I don't think it's so easy to parallelize that. But the local step is super easy to parallelize, right? Because all the springs you can be projecting at the same time. Trivial to do. So yeah, if I should write it explicitly, you would set the di to be pi1 minus pi2 divided by the norm of that, pi1 minus pi2 times the rest length of the spring. So the funny thing is that in the local step, you are actually solving non-convex problems. This is a non-convex optimization problem, but it's a special case of the non-convex problem which we can actually solve quickly and exactly. So we are really benefiting from the fact that here we can do the back substitution, which is efficient, even though not so easy to parallelize. And here, the solve of this non-convex problem is also efficient. And we alternate, we iterate these things until convergence. And modulo the local minima issues, it converges to exactly the same thing as if you run Newton's method. The local minima non-convexity, even it's taking a little bit different path. So in theory, it could lead you to different local minimum. In practice, we never observed it, but you could probably construct some contrived case where this does converge to a different solution. But that's only because of the because of the original energy being non-convex. That's what's the fundamental problem there. Oh, by the way, did I mention one thing I should have probably mentioned before? Oh, I think I mentioned this, right? That the other way how you can make Newton behave better is by decreasing this h, right? Because if you make the h smaller and smaller, ultimately, if you ideally would make it 0, making no time step, but if you made it 0, this would completely go away, right? So if you make it small, close to 0, then this non-convexity doesn't bother you so much, right? And that's essentially how everybody was doing this before. Just lowering the time step, right? You don't really want to be lowering the time step because then you have to do lots of steps until you get some progress, right? So that's why these techniques are interesting. Okay, what we should look at now is how does the convergence of this local global alternation, that's how we call it, compare to Newton's method. So let's take a look at that.
How many steps do you need before it converges, generally?
That depends, right? That depends on the system. How many degrees of freedom do you have? It depends on the configuration. It depends on everything. But what we can do, we can take one state, like this was some hanging curtain type of scenario, right? With some number of degrees of freedom. I think here was like 10,000 vertices or something, or 6,000, something like this. And we can compare on one state, how will the Newton do versus the local global, okay? So this is a relative error. This is similar to what I was showing here, except that it's normalized. So we are starting at 1. That's not a big difference. And here you can see the speed of error reduction. Okay. Notice that this is also a log plot. So this is actually log plot. Okay. So here it looks like that the local global method is not so good, right? Because here it needs, I don't know, like 300 almost iterations, right, to get to the same accuracy as Newton gets in 8 iterations. Okay. But Newton is always solving a new linear system, right? It always needs to refactorize the Hessian if it's using direct solvers and so on. We picked a situation where the non-convexity was not a problem. If it was, you would have to be regularizing, and this would get also even more expensive. So this is actually not a very realistic comparison. The right comparison you should be looking at is the same graph, but on the x-axis now we have a computational time. Because each iteration of our method is much faster, so you can do multiple iterations of our method within the time you would need for 1 Newton iteration, okay? And that's what this graph does. So now it matters what linear system solver do you use in Newton, because each of them has different performance, right? Here it didn't matter because I was just doing iterations of Newton, so I just assumed that the time to solve the linear system is constant, which is of course not true. So it turned out here, that's I guess why I'm recommending direct solvers all the time, that direct solvers perform a little bit better than preconditioned conjugate gradients. That's what people were using before, like Borov-Witkin is recommending PCG. But I think since then, since Borov's times, the direct solvers has gotten better. So we can essentially ignore this because this one gives us better time. And here you can see a very interesting thing, and that's the whole point of this work. Initially, it reduces the error faster than Newton. That's very cool. If you are in real-time physics, all the time you have is like here. If you have 30 milliseconds and you just want to compute as accurate a solution, you really want to go for the local global solver, because it just gets you a much more accurate solution than Newton would in that limited amount of time. Okay. Now, to be fair, Newton will ultimately enter the quadratically convergent phase, as I was telling you about earlier, and then it will beat everything, right? Then it will smash our solver, right? Then we'll just go to the solution, the accurate, exact solution, very quickly. Okay. But take a look. Where did that happen? Where do these curves meet? In this one example, right? But for different examples, it's probably similar. This way, here they meet like, so there will be something to 10 to minus 11, right? And if you are computing your physics simulations to 10 to minus 11 accuracy, then you are being really meticulous, right? This would be something like a nanoscale or something in your simulations.
So here's a suggestion. Why don't you do however many steps?
Yep.
Where your error level is basically within that the Newton's,
and then switch, right?
And then switch, yeah.
Yeah. That's an excellent idea. We should do that, but nobody, as far as I know, has done it yet. That would be an interesting question there. Where exactly do you want to switch, right? It's not completely trivial, because you don't want to be solving the Newton as well, because then you'll be paying twice the cost.
Well, I mean, it looks like, based on this graph, it's kind of where the arrow points, right? To say Newton.
Oh, you mean here? I mean, this
like,
arrow just like pointed wherever I wanted to put this.
Yeah, but when it starts to like really just head down fast. Because then it seems like you're pretty close to a solution. And
that's an excellent idea, and I think we should do it, or somebody. Somebody, yeah. So what you would want to, if you wanted really exact solution, or up to numerical precision exact solution, first run our method and then switch to Newton at some point, right? The only tricky part is where exactly is that point? How do you detect that now is the time to run Newton, unleash Newton?
True. Yeah.
that would have been actually also a great final project. I should have thought about this earlier. Maybe you can sneak it into yours one. No, that's okay. Yeah, we put it there as one of the directions for future work, but I don't think that anybody has done that yet.
So this time step, so this time in seconds is time per iteration?
No, this is
Or is this time for reducing the error?
correct. This was. Yeah, no. I mean, this is just the error per iteration, right? But each iteration has different time cost, right? So here we just, this is per computational time, right? You just run the program and you see how the error is decreasing.
Is
That
this inclusive of, so is this taking into account the pre-computation?
no.
And
That's how we win, right? We assume that the mass spring system you are simulating is not changing.
correct. So like adding, so shouldn't we add the pre-computation time to these?
But the pre-computation time is only one-time cost, right? What you do, you set up your mass spring system, you pick some number of mass points, you define some springs between them, and then once and for all you do the pre-computation. You don't ever have to change the pre-computation until you start tearing or changing masses or doing things like that.
So it looks as if, like when it's like 10 to the minus 6 is when you want to switch it over, and that, obviously.
Yeah.
Either way, I mean, it looks like you're going to get a much better convergence.
Yeah, I mean, this needs to be interpreted with a pinch of salt, right? Because this is for one specific example, for one specific configuration. If you actually this is not a proper analysis, right? This is more like an anecdotal evidence. This might actually even be like a really good case, right? There might be also some cases where it didn't work out so well. I don't remember the details of the data, but that would be how would you do this research, right? You would collect a bunch of simulations. You would see how does it perform on average. As far as I know, nobody has done this. That's an open research problem. Okay, so what I want to show you next is the video. I guess I still have a little bit of time, right? So I can actually show you visually how does it converge. It's in our submission videos. I invite you to watch also the projective dynamics video, which is a more recent paper, so it's a little bit better done. But the cool thing I wanted to show you here is that even if you do just one iteration of the local global step, it already gives you something reasonable. This is just a toy. It's just to show that we can do some cloth sims using this. And it works. Huh? Tintin did this animation. Yeah, the mockup is not his. That's I think from the Berkeley ArcSim thing. So again, this needs to be interpreted with a pinch of salt because it doesn't have to converge to the exact same thing. But this is what I wanted to show you. This is doing just one iteration of local global per frame. And it's certainly far from the exact solution, but it's doing already something much more reasonable than explicit Euler would be doing, right? It's not exploding or anything. It's even doing something much more reasonable than PBD would be doing. I guess this is a good point. You know what? You can watch this on your own. This is on YouTube after all. Let me comment on the difference between this solver, the local global solver, and PBD. The advantage our solver has is the global step. Okay, because the global step essentially can resolve all the translations immediately. That's what you saw. That's what you see on this curtain here. Right here. So what we are doing here, we are these. Let me explain the scenario. These are 2 points which are constraints, which are moving back and forth. And the beauty of the global step is that the translational changes propagate immediately through the entire mesh. Because this global step solving this constant linear system has the power to immediately translate the entire thing, which is much more powerful than PBD, because with PBD, if you translate, then you are running the Gauss-Seidel, and you have to be iterating until the translation propagates. But here, the translation propagates immediately. So that's a huge advantage of this solver. At some point, we also have a comparison to PBD. You probably also already have to go, so you can watch the rest of the video by yourself. Here is a comparison to PBD. So here are sort of highlighted the problems of PBD. Here is PBD, here is our method. As you keep increasing the number of iterations of our method, we converge to the exact implicit Euler solution. If you keep increasing the number of iterations of PBD, you actually converge to a rigid body. And you also need way more iterations with PBD to get there. On the other hand, the iterations of PBD are faster because you're not doing the back substitutions. You're essentially doing just the projections. Okay, so essentially our solver is somewhere between PBD and Newton's method, and we argue it's very good for real-time simulations. So that will be all, unless you have some questions.